Okay, so today we are going to do a lot of little different things that are going to start us down the road to reacting carbonyls. So here is our plan. We're going to talk through the bridge, which is a reflection of the video, which was kind of one new electrophile and a bunch of old nucleophiles that we knew. We are going to go through a new electrophile and talk about how it reacts with nucleophiles. And then we're going to learn about a new nucleophile and how it reacts with electrophiles. We'll see how this fits into at least one reaction in biochemistry or bioorganic mechanisms. And then we'll look at how this stuff fits into retrosynthesis. So we're going to try to apply really only 1 to 2 new reactions to expand our thresholds in a lot of different directions today. So were there any questions on the bridge? So we're not going to spend a lot of time on these reactions. These were pretty hopefully straightforward, and most of you got these, at least the question number 1. No questions. All right, so let's go through these. It is very important that when you see lithium aluminum hydride, you know what that means. So tell me what lithium aluminum hydride reacts like. 1, 2, 3, go. H minus, great. So when you see it, either mentally or physically, cross it out and consider it to be H minus. All right, what about sodium hydroxide? Mallory, what does the sodium do? Right, and so what's left? Correct, with what charge? Correct. All right, Yesenia, when we see this whole magnesium chloride thing, this is a Grignard reagent. What does it react like? Correct, carbon with a negative charge. So this is 4 carbons. I'm going to go ahead and number these. 1, 2, 3, 4. We'll number all of our carbons while we're at it. 5, 6, 7, 8. But this chunk right here, the Grignard, you can kind of mentally or otherwise cross it out, and it reacts like a C minus with the same number of carbons. All right, so all of these are electrophiles, which is our carbonyl, C double bond O, reacting with nucleophiles, which are these negative charges. So it's nucleophiles and electrophiles reacting together. We know, hopefully we remember, that a carbonyl, the main reactivity is that your carbon in your carbonyl is an electrophile. This is something that you guys identified pretty well for our essential outcome for last semester, which was identifying reactivities. Carbonyls are electrophiles. The oxygens pull the electrons away from the carbon, so the carbon doesn't have enough electron density, needs more electrons, loves more electrons, is an electrophile. Everybody good with that? Okay, so the carbonyls electrophiles are the main thing that we'll be looking at today. And that's the main thing we'll be looking at Monday as well. So what's going to kind of tie all of this outcome 5 together is that this is all reactions of carbonyls as electrophiles. So something's going to attack them, and the something that attacks electrophiles is always what? Timothy? Nucleophiles, correct. So we're looking right now at multiple different nucleophiles and considering what they can do. All right, so the first nucleophile we have to consider is this lithium aluminum hydride, which reacts like H minus. It's going to attack the electrophile, kick electrons up. And at least for the moment, that would give us an O minus. And now we would have a new hydrogen attached. So this part right here is new. We have, in terms of energy, started off with what negative charge? Letitia, what negative charge was in my starting material? All of this is your starting material. What's that? So there is 1 negative charge in this circle. What is it? Right, the H minus. So we basically started off with an H minus. And what did we end up with as a negative charge? O minus, yeah. What's more stable, H minus or O minus? Yes. So in case, I know it's been a while since we've done reactions. It's been a while since we considered a lot of these different terms, but generally taking a glance at the periodic table, when you're within the first row, the farther they are to the right, the more electronegative they are and the more stable they are with a negative charge. So O minus is more stable than N minus by a lot. N minus is more stable than C minus by a lot. And H minus is about the same, but H minus and C minus are really, really, really unstable. Then N minus is much more stable. Then O minus is much, much more stable. And then fluorine would be much, much, much more stable. So comparing these two things, essentially in this reaction, we went from an H minus, which is really unstable, to an O minus, which is much more stable. So this goes down in energy. It absolutely favors a product, and it would go for sure towards products. Everybody good with that? All right. In our second reaction, we have an O minus, which is a strong nucleophile. Previously, at least last semester, we didn't add much nuance to this. We just said negative charges are all going to be strong nucleophiles. We're going to add a little bit more depth to that idea today. But O minuses are strong nucleophiles, and they can certainly attack electrophiles. So Chloe, what will we get from this reaction here? Yep, so that O, the existing O would kick up and be negative. And what am I making a new bond to? What's attacking? Right, so I would have another OH here. So this is my new thing that I added on right here. All right, so looking at my combined starting materials, what did I start with in terms of my negative charge, Chloe? Yeah, O with minus charge. And what's in my product? Another O with a minus charge, right? So here I've kind of gone from O negative to O negative. And I'm not going to ask you the trick question of which is more stable. It's about the same in terms of stability. We haven't talked a lot about entropy in this class. You might remember the idea of entropy or degrees of freedom in the first and general chemistry, but suffice to say, having more molecules gives you more sense of chaos than fewer molecules. And so the starting materials are actually more energetically favorable than the products here. So this reaction doesn't prefer to go forward. And if it does, it just kind of goes backwards. So this is not going to have a star. This is not a reaction that is really going to go forward. All right, our last reaction here. So Miguel, what's my nucleophile specifically for this third reaction? Four carbons, so butyl. Right, so this carbon number 4, which was the carbon attached to MgCl in your Grignard reagent, that's the one that's your nucleophile. So which number is that attacking? Right, or correct. So this is going to go right here. So even though I've drawn this carbonyl upside down, you're still attacking the electrophile and kicking those electrons over. So our product would have still the 7, 8, or 5, 6, 7, 8, with an O minus. Then you'd have a new 4 carbon chain attached there. So I'm going to go ahead and number my carbons just to make sure I've got them all. This was my pre-existing 5, 6, 7, 8 of my electrophile. This is my 4, 3, 2, 1 of my nucleophile. So looking at charges, what charge did I have more or less in my starting material? Correct, and in my product? Right, and which one is more stable? Absolutely, by a lot. So we started off here, we'll look at all of them together. Here we started off with a C minus and went down to an O minus. So this one would also absolutely go forward. So these are not the only possible nucleophiles, but I want this one here in the middle to kind of be a representation of all of your other strong nucleophiles. So H minus is incredibly unstable and a fiercely strong nucleophile, stronger than our strongest nucleophiles from last semester. O minus is strong, but it's actually not going to get anything done when it reacts with this particular electrophile. The C minus of a Grignard is fiercely strong and incredibly unstable and will absolutely irreversibly attack a carbonyl. So it turns out that while there are many, many things that will attack and kind of go backwards, there's really 2 strong nucleophiles that are so much stronger than the rest that they will irreversibly attack a ketone or aldehyde. And they are the Grignard and lithium aluminum hydride. So we're going to kind of classify these things as our strongest nucleophiles. You can kind of come up with any term you want to, but it's not just that they're strong nucleophiles and weak nucleophiles. It's a gradient, and there's various degrees of strength. But we're going to add kind of one pot. and say that we have these, I'm going to write it up here, kind of fiercely strong nucleophiles. And they are going to directly attack carbonyls, and it's going to be more or less irreversible. Reversible. Oh my gosh. All right. And those are your C minus and your H minus. So for an H minus, we use lithium aluminum hydride. And sometimes we'll use sodium borohydride, which is something that we don't use as often. We saw it last year in a couple different reactions, but more or less, these guys are both just H minuses. These are your fiercely strong H minuses. And we also have some versions of a C minus. The one that we have done already is RMGX, which is approximately going to react like R minus. And there's another one that does about the same thing. These are used exchangeably. Alkyl lithium, it's going to work the same way. Any carbon group, you could attach a lithium to it the same way you could attach magnesium chloride, and it's just going to act like a fiercely strong C minus. So you can kind of consider this one here to be an afterthought, but basically this one acts just like a Grignard in the way that sodium borohydride reacts exactly like lithium aluminum hydride. There's a slight difference in their strengths, which we'll get into a little bit on Monday. In these two, there's a slight difference in whether they're a stronger nucleophile or a stronger base, but suffice to say, they both act like a fiercely strong C minus. Grignard is what we will use most of these two, and lithium aluminum hydride is what we will use most of these two. So these are the two that I showed you today. These were the two on your bridge. Pretty much everything else would attack a carbonyl reversibly. All right, any questions? So what we have seen now is for today and for this semester, we're going to spend a lot more time with carbonyls as electrophiles, as opposed to alkyl halides. With alkyl halides, which we did a lot of last semester, that was our electrophile last semester. What was your leaving group with an alkyl halide? The halogen. And when a halogen came off, it was negatively charged. And those big halides, which are both electrophile and big, were more stable as a negative charge than pretty much anything else. So if we attacked with an O minus, we would turn an O minus into, let's say, a Br minus, and Br minus is more stable. So with alkyl halides, pretty much any strong nucleophile will do about the same thing. They'll all attack. But with carbonyls, well, kind of your leaving group is an oxygen, which becomes an O minus. And so now we've got something that's not super stable as a leaving group. And therefore, only some nucleophiles, the strongest of nucleophiles, will work to directly attack them. So that's why this is a little bit more complex than what we did in the fall. All right, questions? Okay, so what are my two fiercely strong nucleophiles that are going to attack irreversibly at that carbonyl spot? H minus and C minus. Right. Everybody good with that? Okay. So let's move down and look into a brand new version of an electrophile. So this is an enone because it has both an alkene and a ketone in the same molecule. You might remember we had an enol last semester, which was an alkene and an alcohol. This is an alkene and a ketone. So not just the molecule that has those two things, but has them conjugated, or double bond, double bond, all near each other. All right, so to back up just a second, if we just had straight up a ketone, we would have one resonance structure of that, where the oxygen pulls harder on the electrons than the carbon, so the oxygen can pull away the pi bond. As a reminder, the only thing you can move around in resonance structures, lone pairs and pi bonds. So in this case, the only thing we would have to do is move the pi bond. And that would, if we move the electrons up, give us an O minus and a C plus. And with a resonance structure, remember that the truth is somewhere in between. And so all carbonyls have that carbon that acts kind of like a partial plus. And this is nothing really hopefully new or groundbreaking. What it's telling us is that that carbon doesn't have enough electrons, the oxygen has extras. And that's why that carbon is an electrophile in the first place. And that's what you guys did up until today. You attacked that carbon because it was electrophile. Sound okay? All right, so let's go down and imagine this one. So first off, let's do that exact same thing. If I move those electrons up to the O, I'll see that I have a resonance structure with an O minus and a C plus, which is telling me, once again, that the carbon down here is an electrophile. It's been a while since we drew a resonance structure, so if you guys messed that up a little bit, it's okay. But how are we feeling? Most of the problems came when you tried to do everything at once and missed this resonance structure right here. All right, but here we have a C plus next to a double bond, so we can also hop the double bond over, which will give us a third structure in which we have the carbons are arranged in the same places. None of the single bonds have changed. The double bond moves over here, which gives us the plus charge on the far left. So in any subset of resonance structures, you have all of these things existing at the same time. So while for any ketone or aldehyde, we have an electrophile at this carbon right here, the one down at the bottom, which is partially indicated by the fact that the resonance structure has a plus charge there. In an enone, we also have an electrophile at that same spot. I'm going to redraw my enone. So I have an electrophile at this spot right here. All right, and that was indicated by this resonance structure showing us that I have a possibility of a positive charge at that specific carbon. So based on these resonance structures though, where else do you have a partial positive? Timothy, where else do I have a partial positive or a positive charge in these three structures? Besides right here. Yeah, so this carbon is the one on the far left. So you also have an electrophile right there, which is different, but they both exist simultaneously. And so with an enone, which is a new electrophile for us, not only do you have the electrophile in the carbonyl, but you also have the electrophile at this beta spot. It's 2 carbons away. So when naming, we talked a little bit about this kind of common naming or nicknames, where beta and alpha is the carbon directly next to a carbonyl, beta would be 2 doors down. Well, it turns out if you have a double bond right next to your carbonyl, then you'll have an electrophile at that beta position, or 2 carbons away. So you have 2 simultaneous electrophiles. So we're going to flash back again to something else that you may not love, but hopefully you'll remember. This is not dissimilar to the situation we had with epoxides. Remember, with epoxides, we had 2 different electrophiles at the same time, and we got to choose the conditions that we added to our pot. And under certain conditions, you would attack the less substituted side, and then under different conditions, you would attack the more substituted side. Everybody remember that that was true. So it turned out that what you added would choose which side to attack. And the same thing is going to be true of our enones. Depending on what you add, they will either attack directly in the carbonyl or they'll attack at the beta spot. Before we move on, I need you guys to tell me what 2 fiercely strong nucleophiles directly attack carbonyls? C minus and H minus, and that is still going to be true. So there are only 2 strong, fiercely strong nucleophiles that are going to do that direct attack in the same way that they did above. So your C minus from your Grignard or alkylithium is going to directly attack a carbonyl, and your H minus from lithium aluminum hydride or sodium borohydride is going to directly attack your carbonyl. And those are still, and will actually always be, our 2 fiercely strong nucleophiles. Every other strong nucleophile is going to do something different. All right, so we're going to move on and start a brand new page here. Any questions on this before we move in? I know this might seem like we're hopping all over the place, but all of this stuff is related. We're looking at attacking carbonyls, but the enone is different variations on attacking carbonyls. So we're going to share a whiteboard, and we're just going to focus right now on this enone. All right, so there's two different ways of doing it. If you start with that enone, your fiercely strong nucleophiles which were H minus, or really that C minus from Grignard. Those are our four, these fiercely strong nucleophiles. They're all going to do what we call direct addition. So they're all going to, whichever one you use, is going to just do what we did on the bridge. They're going to straight up attack that spot right there. And your nucleophile will be attached right there. So if any of these are your step one, then your step two would be to protonate. You would have the double bond effectively does nothing. You're going to have whatever that nucleophile was attached at that direct spot at the electrophile, because that's what they do. So think of these as being so voraciously interested in attacking as quickly as possible that they just go to the simplest place, which is right into that electrophile, and they're going for it, and they don't go backwards, and they're done, and they're quick, and they don't take their time to evaluate their options. They just do grab the first thing they can find. They're split decision makers, and that's what they get. So this is not new. This is the exact same thing we saw in the bridge. All right. That sound good? So that's the same as before. So here is the difference. If we start off with this thing, and let's say that we use, I'm going to go ahead and use hydroxide, because hydroxide is one that we used on the bridge. So let's classify these guys as compared to these fierce nukes. These are going to be strong, but less fierce nucleophiles. So we're going to have pretty much every other nucleophile fits into the second pot. They could directly attach to the carbonyl and kick electrons up. But as we saw in the second problem on that bridge, what happens? It goes back and forth, right? So it just goes backwards. They can attack, but then they go backwards. So think of these guys as kind of being choosy. They would attack there and then go backwards. But then they can choose to attack again. And they always have those two options because as we saw a second ago, you have two different electrophiles in an enone. You've got that direct place to attack right at the carbonyl, and we call this direct addition. Oops. Well, that looks disastrous. Let's try that again. Direct addition or direct attack. Or we have this conjugate addition where they could instead attack that beta spot. So if they attack that beta spot, this is the alpha beta, well, what would happen is it would kick that double bond over. This should look a lot like the resonance, and then simultaneously kick electrons up to the O. So electrons do go up to the O, just in a little bit of a roundabout way. Your OH minus, or whatever kind of weakish nucleophile you have, is going to be attached at that beta position instead. This might look a little weird, like why would you bother stopping there? But we usually do these since we don't have something like lithium aluminum hydride or a Grignard. We just go ahead and do this in water. So you don't need a second step of protonation. You got the water in there anyway. And so this O minus would get protonated and it would turn into, and keep my new thing in blue, would turn into this. All right, this is an alkene with an alcohol coming off of it, which is something we saw near the end of last semester, but it's been a while since then. This is an enol, or an alkene and an alcohol together. Anybody remember what enols do? They had this really cool word that started with T. They tautomerize. And tautomerization, I got really excited about tautomerization. Not only is it a cool word, but it's something that happens on its own and gives off a whole lot of energy. It's very favorable. That what they do is they, on their own, tautomerize into carbonyls. So this is not a question mark. This is an equilibria that favors product. So you'll notice that, once again, here's that alpha and the beta. Your new thing right here is attached at the beta spot instead of being attached directly at that electrophile. So whichever way we go, your fiercely strong nucleophiles add on directly to the carbonyl, and they attach to the carbon in the carbonyl. Every other nucleophile is going to attach instead at the beta position, because by attacking here, this first step would be reversible, but this second step of tautomerization is very energetically favorable. So it turns out that by attacking beta, you end up with a much more stable product at the end of the day. And so they would reverse and basically choose both out and pick the one that would be most energetically favorable, which would be attacking the beta spot instead. So I know a lot of people that fit into these two camps, but this is kind of like your fierce nucleophiles are hasty decision makers. They just grab the first thing, they're done, that's it. All right. Every other nucleophile is going to take its time, select from its options, and take a while and pick out what works out best. So again, putting these into two camps, your H- and your C- of your lithium aluminum hydride and sodium borohydride for your H-, your Grignard or your alkyl lithium for your R-, these guys will directly attach. They will directly attach or directly attack a carbonyl either by itself or the carbonyl of an enone. However, if you do have an enone, all of your other nucleophiles, of which I'll make a list here. OH- would be fine, would be one of them. Cyanide, so a C- that's stable enough to exist for a while and be more choosy. This one that we saw earlier this week in lab, your C- at the end of a triple bond, which is not incredibly unstable, so not a fiercely strong nucleophile. That one would work there. OR-. So these are a lot of the nucleophiles that we had seen already. All of these guys will be kind of choosy. And all of these guys would attack the beta spot. And they would end up attached at the beta spot and do what we call conjugate addition. And this is just a term, but compared to directly attacking the carbonyl, which is direct addition, all of this stuff with these strong but not so fierce nucleophiles, this is called conjugate addition. I'm not so worried about the terms as long as you're putting things in the right place. But they would end up attached to the beta spot instead. So this mechanism probably seems a little bit more complicated, but if you just compare starting material to product, you attack or attach that nucleophile directly to the beta and the double bond goes away. So it does kind of kick electrons up to the O, but then they come back again. So the double bond disappears, turns into a single bond, and your nucleophile is attached to the beta spot. When we attacked with a fierce nucleophile, it came in at the carbonyl, and the double bond to the O is what disappeared instead. All right, any questions so far? Okay. All right, we are going to add a carbon nucleophile to this second stack. So this is going to be our new nucleophile for today. It's going to be a Gilman reagent. And I'll write it out on a new page here, but just so you got it in the right spot. A Gilman reagent, which is different from a Grignard reagent, although everybody just names things after themselves. This is going to be effectively our weak-ish carbon nucleophile. And this would also have the pleasure of attacking at the beta position instead. So basically, years after Grignard came up with a carbon nucleophile that was fiercely strong and would do direct attack, Gilman came up with one that was a little bit more choosy. And so by having both at the same time, if you add a Grignard, you can have carbons that directly attack at that carbonyl spot. But by having a more weak and choosy carbon nucleophile, you could also add this one instead and attack at the beta spot. So it's kind of like hammers. We have sledgehammers, we have little tiny hammers. Probably there's bigger hammers, I don't even know. But they all exist and they're used for different jobs. The same thing is true here. A carbon nucleophile, depending on how strong it is, can be used for different jobs. All right, so let's move into Gilman reagents. All right, flashback, Grignard, fiercely strong. A Grignard was a carbon attached to MgX. Magnesium, if you look at the periodic table, is a long way away from carbon. There is a huge difference in electronegativity. Carbon gets basically all of its electron density. Carbon is a fiercely strong nucleophile. In the Gilman reagent, you have carbon attached to copper instead. There's a little bit more to this, but looking at where copper is, you check out the periodic table, copper, which is in the transition metals, it's between nickel and zinc, above silver and gold. It's significantly closer to carbon, and so the gap in electronegativity is much smaller. So while the electrons are going in the direction of the carbon, it's not as fierce, it's not as differentiated. So this carbon has a smaller negative charge, whereas this carbon has a very large negative charge. Well, copper by itself won't make a covalent bond to a carbon. So it turns out that it needs to hook up to two carbons at the same time and also lithium. This is what Gilman found works. So while a Grignard only has one carbon and it reacts as if it is a fiercely strong R minus, the Gilman reagent acts as if it is a, I don't know, choosy, less fierce, weak, or mildly strong? Version of the same thing. You can kind of choose whichever term you want there. Just thinking about it though, it's more choosy. It's a weaker carbon nucleophile, but it's still a carbon nucleophile. It is a little bit weird that you have two carbons on here. You would want to use the same carbon for both, because if you had like an ethyl on this spot and a methyl on this spot, you wouldn't know which one would attack. So when we make Gilman reagents, we have two of the same carbon chunk attached. Since we don't know which one will attach, it doesn't matter if they're both the same. So with a Grignard, you only need one carbon chunk. To make a Gilman, you need to have two carbon chunks. It's not the end of the world, but they end up being two of them attached, but only one of them is your nucleophile. So if we were to start with that same, actually, let's do a different enone just to spice things up a little bit. This one's going to be in a ring, but it's okay. Here is your alpha carbon and your beta carbon, and you do have that double bond. So you do have an enone, and we have two different electrophiles. We could attack directly at the carbonyl, or we also have an electrophile at that beta position. So let's look at our two different possibilities. I'm going to add a CH3 MgCl in my step 1, followed by some water to protonate it in step 2. All right, Mallory, Grignard acts like what? Yes, this is a fiercely strong nucleophile. It's going to act like, in this case, I just had a methyl group, so it'd be a CH3 minus. And where would that attack? Correct. That very first kind of double bond O electrophile. It gets right up in there. And my product would have the exact same 6-membered ring. The double bond in the ring would be in the same place because it didn't mess with that. And I would have a new CH3 attached right there. Everybody good with that? So this is exactly the same thing from the bridge. It was kind of our very first nucleophile attacking the carbon. All right, if on the other hand, I chose to add, here, I'll start with the same thing. We've got that alpha beta, we call this an unsaturation, but it's just an alkene. I've got two electrophiles, one directly at the carbonyl and one at that beta spot through resonance. And let's add instead a Gilman reagent. So we'll do it once again with methyl. We need two of these and then copper lithium. That would be our step 1, and our step 2 would be water. Or acid, either way, protonating is easy. All right, Yesenia, so what does this combination act like? Yeah, so it still acts just like a C minus. So because I've got just methyl groups there, there's two of them, because you have to have two of the same thing here. It's once again gonna act like a CH3 minus. But in terms of reactivity, your Grignard is a fiercely strong C minus and does the direct attack. Your Gilman is a much milder or choosier one. And so where does this one attack? Right at the beta spot instead. So that would go in down there. And if you want to, you can draw this all out basically from a mechanism point of view. This might be confusing if in your notes. So just stop a second and you can choose what to do. So kind of here's what happens. You attack there. We put all of this on the previous page. These electrons would go up there. This would go up there. But then this comes back down again, and this one swings back over there. So it kind of moves everywhere. So I would actually advise a little bit against drawing all that mechanism out. You can just do this if you want to, or you can just stop there. Because at the end of the day, your methyl group is just going to attach at the beta spot. And so in your product, nothing happens to the carbonyl at the end, even though something happens over the course of the reaction. And you would just have a CH3 attached here at that beta spot. So we get to choose. If you want your carbon to attack an enone at the beta spot, you should use a Gilman reagent. It's more choosy, and that's what it would prefer. If you want your carbon nucleophile to attack at the carbonyl, you should use a Grignard or an alpha lithium instead. This is where it will go. So you control where you want your nucleophile to attach. All right, any questions on that stuff? Yes, sir.
Where does the alkene go then?
Where does the what go?
How does the alkene go away basically?
So basically what happens, let me back up a second. What happens here is the double bond goes away because the electrons go up and make an O minus, which then gets protonated, turned into an OH.
Okay.
Down here, basically those electrons go up to the alpha spot, becoming a C minus, which gets protonated, turning into a CH. So in both of these cases, I went too fast. Let me go backwards. So this is mechanistically what happens. When you attack the beta spot, the double bond shifts over and the double bond O turns into an O minus. But when you protonate the O minus, it becomes momentarily an enol, which then tautomerizes, and the double bond actually moves back to where the double bond, to restore the double bond O. Yeah, so weirdly, this double bond O kind of goes up to form the double bond O up there, and the double bond O disappears. But if you just look at the starting material and the product, it kind of looks like the double bond O, nothing happens, and the C double bond C just turns into a C single bond C. So that's kind of what we shorthanded here. And our new one, we just said we attack that C double bond C, and it just turns into a C single bond C. When you attack the C double bond O, it turns into a C single bond O. So when you attack a double bond, it becomes a single bond. If you attack the double bond O, it becomes a C single bond O. If you attack the C double bond C, it becomes a C single bond C. But this is, you know me, I love the mechanisms. I love these stories. But this is one where I think it's much more simple. If you just slap it on the beta and get rid of the double bond. The story was confusing and doesn't really go anywhere. You good with that? Okay. All right. So this was the story of our new electrophile. It had two choices, and it depends on how strong your nucleophile is in terms of what you get at the end of the day. Questions? All right, Miguel, I've got some trick questions for you. You ready? Okay. Over on this side, I have an alpha beta carbon as well. Why doesn't anything happen at this beta spot?
Both those carbons are already bonded to hydrogens, so if anything were to happen, it would mess.
Yeah, it's not an electrophile because you don't have a double bond. There is nowhere to attack. There are no resin structures. Lovely. Okay. I'm going to ask another trick question. Here, I'll start with this thing. If I were to start with that, which is just an aldehyde, we know already what kind of nucleophile attacks it. So what if I added a Gilman to not an enone, but just straight up a carbonyl? Chloe. What are your thoughts? A Gilman is not a Grignard. A Gilman is a weak version of this. So let's think back of this in terms of a little bit of process of elimination. We had two nucleophiles that were strong enough to do direct addition to a carbonyl. What were they? The fierce ones. Yeah, so the H- of LAH or the C- of specifically a Grignard. Do I have either of those? No. So if those are the only ones that will reliably do irreversible direct attack of a carbonyl, will this do direct attack on a carbonyl? No, correct. So will anything happen? No, correct. So much like that second reaction in our bridge assignment, where you could add an OH-, would it attack? Maybe, but it just goes backwards. Would this attack? Maybe, but it just goes backwards. So are you gonna get anywhere? No. So this Gilman reagent will not directly attack a ketone or an aldehyde. You would get no reaction. Because once again, the only things that will directly attack a carbonyl or from a ketone or an aldehyde would be a Grignard reagent or an alkyl lithium aluminum hydride, or sodium borehydride. All of these other nucleophiles could attack, but they just go backwards. Good call. So what would I need in order to have this thing join on? Where does it attack? Anyway.
Double.
Right. Okay. Would it work? This is another trick question. Would it work if the double bond was right there? It would not. It only works if you have that resonance. So it only works if the double bond is conjugated or right next door to the double bond or to the carbonyl. So here, nothing would happen this way either. The only way it would work is if you have the double bond from the alpha to the beta. That's the only way it'll work, and it would only work at the beta. So it's actually, there's not, your Gilman has limited usefulness, but it's really good in the kind of couple circumstances in which it works. A Gilman is something that we're going to use for really two reactions. One that we just did today, and another one that we're going to do on Monday. So Gilman is a very specific tool used in very specific circumstances, which only really works in a couple niche purposes, but is great when you're in those circumstances. All right, questions on that? This whole thing turns out to be really helpful for us on Monday, which is why I wanted to bring it up. All right, we got two more things to talk about today. First off, I want to go backwards a little bit and show you that what we're really doing here is addition. So just kind of, you can flip back a little bit, but notice that you added a CH3 at that beta position. Anybody remember what we added at the alpha position? Because something's on there. Came from the water when we protonated. Yeah, hydrogen. So you actually did add two things. There's a CH3 and an H. When we attacked with one of these fierce nucleophiles directly at this double bond, the double bond went away and we added a CH3 to the electrophile. What did we add to the O? a hydrogen. So it turns out that you add something to both sides of the double bond. So it is an addition reaction. We did a lot of addition reactions last semester. We went through them in retrosynthesis on Monday. You could add X and X, X and OH, OH and H and X, all these come, two OHs, all these different things. Those were all catalyzed by electrophiles. These guys start off with nucleophiles, which is a little bit different. The other thing that's different about these is these are polar double bonds. And so carbonyls are kind of the classic versions, but it's still an addition. When you get rid of a double bond, you add something to both sides. All right, so when we were doing some naming, I'm bringing everything in here. One of the molecules I asked you guys to name, I think it was on Monday, but we were looking at carboxylic acids. And one of the examples I brought up, you don't have to remember this, but was this molecule right here, which was involved in the citric acid cycle. This was fumaric acid. And I asked you guys to give the IUPAC name of it, but that's not what we're worried about right now. So fumaric acid in the citric acid cycle. So citric acid cycle, this is part of why we breathe. We breathe so we have oxygen for oxidative phosphorylation, so we can process all these electrons we get out of the citric acid cycle. That's where most of our energy comes from, not glycolysis, but the citric acid cycle through oxidative phosphorylation. Biology, it's a thing, it's great, we're alive, that's fantastic. But one of the steps is you start with fumaric acid and we turn it into malic acid. Most of the time these acids are deprotonated, so they're O minuses instead. So you probably get used to more seeing this as fumarate and malate, but I'm gonna draw them with a neutral species. All right, so what is different between this molecule and the product over here? Letitia, what have we done? All right, so we converted it into alcohol. So we added an OH over here. What did we add right here? Yeah, a hydrogen. So really what we're doing is we're adding an OH and an H to a double bond. So I don't expect you to remember these, but when we were adding OH and H to an alkene, we could do it Markovnikov or anti-Markovnikov. Markovnikov used, anybody remember those reagents? It's okay, mercury diacetate followed by, and sodium borohydride. And if we wanted to do it anti-Markovnikov, it was that borane BH3.THF followed by hydrogen peroxide, all that stuff. You don't have that in your cells. So while we could do that in a little jar or a little round bottom flask in organic chemistry, that's not how we do that biologically. Well, the cool thing about this double bond is it's not just a double bond, it's a double bond that is conjugated to a carbonyl. So it's actually, it's not a ketone, but it's that alpha beta directly right next to a carbonyl. So instead of doing this with some metallic electrophile, we could actually do it with a nucleophile. And if we want to attach OH or H, which one of those is way easier to have as a nucleophile, an H minus or an O minus, which is far more stable? O minus, yeah. So biologically, all we really need to do is have something that acts like O minus. And in the enzyme active site, you can just take water and have some type of basic amino acid pull the hydrogen off and momentarily make it an OH minus. Well, that is going to do that beta attack because this is a strong but not fierce nucleophile. So it attacks that beta spot. And once again, we could kick the electrons up to the O and swing them back down again, or we could just imagine this thing grabbing an H from a water. And you end up with an OH on one side and an H on the other. And so this step of the citric acid cycle is just exactly like what we did in class today. You got an OH minus, it attacks the beta spot, which is a better electrophile energetically at the end of the day. And attacking carboxylic acid is not as stable anyway. So that's how we add this on. And we actually can model the enzyme active site and find that it puts a water, which it deprotonates to become an OH minus, really close to that particular place. And because enzymes are like gloves and they can put stuff in very specific spots, it does it chirally and only attacks from one side and not the other. So it makes a chiral product for you, which is really cool, because that's a chiral carbon. So all of these reactions that we're covering in this class, in an ideal world, we will have enough time to go through every step of the citric acid cycle and glycolysis. And what you'll find is that it's a combination of the reactions that we're covering in this course. It's a lot of nucleophile electrophiles, a lot of acid base. There's leaving groups. It's the same stories. It's the same kind of things. It's the same mechanisms, electrons moving in those same directions, which is really cool. This is some of what I like about biology is I get to apply organic chemistry, but maybe for you to go the other way. Hopefully, if you see how the organic fits into the biology, you can kind of see why it matters. So I'll try to splash in as much biochemistry as I can kind of during our classes. But questions on that? I'm not going to ask you to regurgitate biochemical reactions to me, but I do want you to see how what we're doing right now actually does fit. You guys are doing this in your cells right now. I know that because you're alive. All right. All right, so lastly, let's look at how this fits into retrosynthesis. We've got about 9 minutes left. All right, so if I were to start with, let's say this, I don't know, here. I'll make it fancy. I'll put a ketone with a benzene ring, whatever. And I'm gonna add into this lithium aluminum hydride. So this was one that was more or less on your bridge. Lithium aluminum hydride acts like what? H minus. And H minus, is that a strong nucleophile or a fiercely strong nucleophile? Fiercely strong nucleophile. So where's it gonna attack?
Yeah.
Straight up into the carbonyl, right? Whoop, whoop. All right, and let's say that this is step number 1, and we'll go ahead and add a step number 2 where we protonate that oxygen afterwards. So I added an H to the bottom, and then the water let me add an H to the top. What have I accomplished? Big picture. Did I make my carbon chain any bigger? No. Did I make my carbon chain any smaller? No. Did I change my functional group? Yes. So this is a functional group interconversion. I started with a ketone. And what did I turn it into? Alcohol. So you guys have that functional group interconversion flowchart that has a bunch of reactions on it. Well, you already have ketone on there and you already have alcohol on there. So this just basically lets you add a new arrow, starting at ketone, pointing to alcohol, and what's the reagent? Lithium aluminum hydride, LAH, followed by water. So new arrow from something you've got on there to something you've got on there. All right, what if I started with, well, I love those tert-butyl groups, so I'm going to put one on there, even though it wouldn't be part of the name. This would be a 3,3-dimethyl butanol, but it's an aldehyde. All right, if I were to add lithium aluminum hydride to that, and I'm going to get fancy and I'm going to call it LAH by its initials, it's still the same thing. And then protonate it, draw out, if you will, the product you're going to get. So Mallory, what functional group do I have in my product here? Yeah, it's an alcohol. So lithium aluminum hydride is the reagent that will turn an aldehyde into an alcohol without changing your carbon chain, so just a functional group interconversion. It's also the same reagent that you would use to turn a ketone into an alcohol. It's a little bit different. A ketone would have carbons on both sides of the alcohol, and an aldehyde would have carbons on only one side of the alcohol, because the aldehyde has the carbonyl at the end, so the alcohol will be at the end. The ketone has the carbonyl in the middle of a chain, so the alcohol would be in the middle of a chain. So it's not the exact same alcohols, but in both cases, it's just a functional group interconversion that starts with a carbonyl and turns it into an alcohol. So those should just be two new arrows that you add to your functional group interconversion flowchart. Lastly, today we added two new ways of making carbon-carbon bonds. So one of them is that you could start with a ketone or aldehyde and add a Grignard. Followed by water. And so this would fit into carbon-carbon bond formation reactions. So the way that we listed these out is this is your carbon electrophile. And it couples up with a Grignard as your carbon nucleophile. And it would give you a brand new bond between whatever was your electrophile and the carbon that was your nucleophile. There's your new carbon-carbon bond. So if we did, I guess, reaction number 1 on the board on Monday or Tuesday in lab, this might be your number 2. We did another one a little bit later on, which is that if you started with an enone as your electrophile, that would work with a Gilman. And in this case, you would attach and make a new carbon-carbon bond at that beta position. That's your new carbon-carbon. And so basically these give you just two new ways of making a carbon-carbon bond at different relative locations. They do change your functional groups around a little bit, but the main goal of this stuff is to make a new carbon-carbon bond. So I don't know that we will take the time to do this at the end of every class, but every reaction that we do will be able to fit into one of those two pots. Either it's changing your functional group without changing your carbon-carbon chain, like these ones over here, or if it involves a carbon nucleophile and a carbon electrophile, it'll make new carbon-carbon bonds like these two reactions. All right, any questions? We didn't really cover a lot of reactions today, but we covered a whole lot of new stuff about those reactions. On Monday, I do want to prepare you. We are going to do just a lot of reactions. So watch those videos, get on top of that. I would really recommend that you practice the new stuff before we get in today, but it'll all be very related to what we just did. So thanks. Have a lovely weekend. I'll see you all, I guess maybe in lab or in class on Friday or sometime. I'll see you all sometime next week. Thanks. See you sometime.